In this problem, we are going to see what reagents we need to use to accomplish each of the transformations indicated by the arrow. Okay, so let's go for the first one, the arrow that I have here. Well, I have the metal here the same, but I have a bromine, or even here I have an OH in a different position. What I'm going to do the first one on the bottom, they look very similar. So evidently I need to move that OH from that place. So this reaction happens through a sequence of elimination and addition. So to remove that, we need to remember that OH is a bad leaving group. So what we're going to do is to promote E1 elimination. So first we're going to be using, say, diluted sulfuric acid and heat as, let me do that here, as my first step. In that, I will be making the following alkene. Let me draw the intermediate. So after I do that, I'm going to have to do that step by step. All right. So I'm going to do that over to the other side. Let's say that I do diluted sulfuric acid and heat. When I do that, I am protonating this, and I'll be forming a secondary carbocation. And because we have heat, we will be promoting an E1 elimination, so protonation there first. And this will depart, and you will form a carbocation here. But now notice this carbocation is secondary, and we can make it better by rearranging. And so what's going to happen here is that here you have a metal, what it was. Now you still have a hydrogen, yes? So what we're going to do is a 1,2 hydride shift. In doing the 1,2 hydride shift, and I am going to need more room, so I'm going to copy that elsewhere, the other reaction. And here I have what that I have here. I had it. I'm going to copy what I just erased, okay? Because I'm going back to that. And I had this. All right. So when we were saying that diluted acid, we will first protonate the OH, make it a good leaving group. So this step is loss of leaving group, generating a secondary carbocation. And then here I have a 1,2 hydride shift. And that will give me a tertiary carbocation, which is the following. And at that carbocation, you will have the attack by water. So remember that in diluted acid, you have water. So the nucleophile here will be water under acidic conditions that we have. And that will lead me to the product. So summarizing, I'm going to draw in the arrow what we just used, which was, in here, we used it, sulfuric acid, it was diluted, and we did that, again, lots of leaving group, hydride, and all that, and the carbocation has rearranged, and we formed that product. Okay, so we have that. The path to obtain this is similar. Since we can go from this species by nucleophilic attack of bromide. So what do I need to do here is to add HBr. Because when you add HBr, you will be protonating DOH. You will be forming that. And the parts, so loss of leaving group. But once you have a nucleophile, instead of having the attack by water, to form the other compound, your nucleophile is going to be bromide. So you're going to have bromide. Let me write it in purple. Bromide, this time attacking the tertiary carbocation. Remember here, you don't have a chiral center, so you have only one product. So the path is very similar, only that here we use the diluted sulfuric acid. You generated that carbocation, rearranged. The nucleophile at first for that was water, and for this, the nucleophile, same intermediate carbocation that rearranges, and then you have the nucleophilic attack by bromide. Now, let's analyze the other path that we have here. So what do we have is an elimination. So notice that we have formed a double bond here. So but can we do that? So let's remember how this mechanism works. So if we do, first we know to get there that OH again is a bad leaving group. So my first step is going to be transforming that into tosylate. So I'm going to do tosyl chloride, and I am going to have the following. We're not touching, since the reaction is paratoluene sulfonic chloride is the following. So let me just write it up. Is that's a metal group. And so what we have here is the O at the oxygen is what actually does that. And then you get all of that. This is also chloride, and you will get OTS. But what I want you to see is that in this mechanism, we didn't touch the chiral center. What reacted was the O as acting as nucleophile here. But this stayed the same, so the stereochemistry of that center had not been modified. Oh. Okay, now I have OTS. So, and I need to do an elimination. Here we need to pay attention whether this is possible or not. And for that, I'm going to draw the structure of these in the form of a chair. So here I have my tosyl group up, and it says here that the methyl group is also up. So that's what I want to see, up, they're next to each other. So one will be axial, the other will be equatorial. And you can do that elimination because this is a metal, but you do have a hydrogen that is anti-paraplanar, so opposite side. And I'm going to draw it here. So that product is possible. You have the right stereochemistry. Otherwise, if this metal had been anodized, then it would not be possible to form that. So we have the right, say, structure here, and we can do the elimination. So the next step to get here will be using a strong base. And we can use, for example, say sodium methoxide, and then your base is gonna get the hydrogen. And now you're making a double bond, but right here between where the metal was and the tosyl, right? And that's what you're making your alkene. Yes? And so, again, it is possible because we had the appropriate conformation of that. So this too, the H and the leaving group were opposite in the anti-periplanar conformation. So I was able to make a bond here where the metal group is. So now that I have that, summarizing what reagents I need to go from here to here, I first need to do the reaction with tosyl chloride, and then I will need to use, say, sodium ethoxide to do the E2 elimination. So that's there. All right. So now we have another reaction to complete, this one here. And that's, notice that you need to do an elimination as well. Bad leaving group. So my first step needs to be transform that into a good leaving group. So I'm going to use tosyl chloride again. And this time, I need to use a different type of base because the elimination is not happening towards the ring to get a more substituted alkene, but rather here. That's what we call the Hoffman product. And to do that, that means in the second step, I need to use something bulky, a bulky base, such as potassium terbutoxide. So that is my base to ensure that I have that. But again, strategy similar. I needed to transform the OH, similar to that example here, into a good living group and then do the beta elimination. That's my alpha carbon, beta, beta. But over to that side. The final reaction that I have here involves now an addition to the double bond. And notice it is a hydration because we had added H and OH across the double bond. And what I want you to see is that the H and the OH are added to the same side. It is a sine addition and also is anti-Markovnikov. What that means is the reagent that you need to select that does that is first you do hydrogenation, so BH3 in THF, and then you do an oxidation reaction. So that is a sequence of reagents that we need to use to accomplish all of these transformations.